Good afternoon. The plan for today is continue talking about cache. Last thing that we said last time was we need to have memory hierarchy, and memory hierarchy means that I don't have all the spaces in the world to store everything. Of course, in an ideal world I would, but in reality I wouldn't. So I'm going to get into situations where my memory would be significantly larger than my cache. For now, let's talk about just one level of cache and one level of memory. So I have all my data is here, and I have a smaller subset of memory that I call cache, and I want to store some of this data into that cache. That's the simplest thing. I already talked about the technology and all that. No longer we need to worry about that for now. Just let's talk about like in terms of storage for now, okay? What will happen is that since I cannot obviously store everything into my cache, there will be situations that I need the data and I don't have it. And said that we call this a cache miss, right? And now we need to kind of decide that, okay, how do we do the mapping? How do we decide what is in the cache and what is not in the cache, and so on and so forth. As a result, we said that essentially any cache has two parts. It has what we call a data store, and it has what we call a tag store. Data store is where the actual data is stored. Remember that the cache has to be like, your memory has to be byte addressable and so on. So you can think about each row of this is 1 byte of data, okay? Or maybe it's multiple bytes of data. Later you're going to see that how we design the cache. But what is important here is that we need to have a mechanism to remember what we stored. Going back to this example, as I said, if all of these blue lines are mapped into the same row in the cache, then we need to distinguish and differentiate between each of these blue lines. How do we do that? We essentially store an identifiable and unique tag to each one of them. What is the tag that we should use? You can either use arbitrary numbers, but easier thing would be using the address itself. Using the address that you have in your main memory as the tag inside your cache, okay? So essentially I can store, if I store the whole number here, then I can have a unique identifier. If I see this number, I know that this is the line that I stored. If I see this number, I know that this is the one I stored, and so on and so forth. So that's the idea we are going after, okay? So now let's see how we can optimize and how exactly should we store this. Let's just start with like a simple example of 3 bits, okay? So if I have 3 bits, this is how my memory would look like, right? So this is my main memory, and as I said, for now, assume that we have all the addresses in our design, okay? And let's say the content of each one of them is just a character. It's a byte, so like A, B, C. These are the content, so it's just like 5, 10, 12, whatever, okay? In an ideal scenario, as I said, I can just store everything and then call it a day. I don't need any sort of storage. But let's say I have a smaller cache that, let's say, is half the size of my main memory, right? And the lines in this cache is 0001, 1011, okay? So how should we store the tags? Yes. Yes, this is your memory and this is your cache. Make sense? Mm-hmm. So what should we store as the tag store in here, okay? The first thing that I can store is I can basically store everything here, right? So for example, if I want to store this line, I put 000 here. If I want to store this one, I put 010 here, okay? So I can have 3 bits of a tag, and that would be all I need to store. But remember that tag store itself is memory. So you want to minimize the amount of things that you want to store as a tag. If I can store smaller things to optimize the space, I should do it, because that allows me to have bigger cache, and bigger cache is better for performance. So what do I do? I use this fact that this lower bits can basically be reused for these as well, okay? So essentially what I can do is that I can say that, okay, if the lower 2 bits of my memory is 00, I'm gonna actually assign it to this line. If the lower bits is, for example, 1, 0, I can assign it to this line, and so on and so forth. So all I need to store now is, I know that essentially the mapping of this line and this line would be this guy. The mapping of this line and this line would be this one, and so on and so forth. So what remains of this address is just 1 bit, okay? So all I need to store in my tag store would be just 1 bit, 0 or 1, okay? So for example, if I see, let's say I see something like this, okay? So this would be 0, 0, this would be 0, 1, this would be 1, 0, and this would be 1, 1. If I store something like 0, 0, 1, 1, the data that I'm storing in this first one is 0, 0, 0, and this one would be 0, 0, 1, and this one would be 1, 1, 0, and in this one would be 1, 1, 1. So these are the things that I've stored. I don't no longer need to store all the 3 bits. All I need to store is just 1 bit, because then I can reconstruct the address. So your address becomes something like this, that if you have, let's say, a 3-bit address space, the first 2 bit would be your, what we call the index. This is essentially to index into this table. And then the remaining bits would be your tag. In this particular case, since the entire thing is 3 bits and you only need 2 bits of index, you have 1 bit of tag. What will happen if you had, for example, 4 bits of address? Then you would have like 0, 0 here, 0, 0, 0, 0, 0, 0, 0, 0, 0. Then you would have 1, 0, 0, 1, 0, 0, 1, and so on and so forth, right? You would have 16 different addresses. And here, instead of 1 bit, you would have had stored 2 bits, right? So you would store, for example, 0, 0 here, or 1, 0 here, and so on and so forth. So this way you would be able to distinguish between them. If I have longer bits of addresses, my tag becomes longer, right? How do we increase the index? Index basically increase if I have more rows in this cache. So the number of bits for index is determined by the size of your cache. For example, if I tell you that I only have 4 rows in the cache, log 2 of that will give you the index. If I have 8 rows in the cache, log 2 of that will give you index, and so on and so forth. So that part is defined by the hardware. The rest of it is defined by the size of the address. So for example, if our addresses are 32-bit and you're only using 3 bits for the index, then 32 minus 3 is the size of your tag, right? Yes. Yeah, so this is just the tag store, okay? So this is the tag store. Your actual data is here. So you also have a separate table called data store. The size of this data store is whatever size that you're storing here. If it's byte addressable, you store a byte. If it's 32-bit, you store 32-bit. So this part doesn't change. Regardless of how many tag bits you have, this size does not change. And this size is also depends on the index. So if I have more rows, I'll have a bigger data store as well. Mm-hmm. So the question is, why do I know where it is in the memory? So imagine a scenario like this, right? So let's say this is what you have stored in the, so you have like an address comes, okay? And you want to see whether you have stored it in the cache or not, okay? How do I know this is the data that I've stored in the cache? I need to somehow identify this data because, for example, look at this scenario. All of these blue ones are stored here. So how do you know that it's this one that you have stored, or this one that you have stored, or this one you have stored, or this one you have stored? You need to identify it, right? It's a full address. So it tells you that this is the address that you have stored in the cache, okay? Because there are scenarios, 1 out of 4, like 3 out of 4, you're not gonna have it in the cache. Why the data is spread? This is just one mapping, right? So it could be any other mappings. Let's say, for example, I can do, okay, these first four goes to the first one, this second 4 goes to the second one. This is just a mapping. Later, you're going to see when we are changing the mapping, things are changing. Got a question there? And then. So the question is, when we are picking the tag, why did we use the most significant bit? Why did we index it like this way, and maybe we could have indexed it this way, right? So yes, it's also possible to do it that way. Later on, we're going to talk about like the right strategies. The reason that you want to do it this way is because of the spatial locality. So you want to distinguish between nearby rows. You want to each row to be assigned to a different row so that they don't kick each other out, kind of thing. But we're going to talk about blocks and block sizes. There you're going to see how we make these decisions. So your question? Mm-hmm. Yes. Yes. The content inside the memory. Yes. So you have two things. You have both tag store and you have data store. Okay. So just keep in mind that when we say cache, we mean both the tag store and the data store. The data store just store the data. It's not that interesting for us. The tag store is the one that you design. Data store, it's a memory, right? You store things into it, but you need to know what you have stored because there are multiple lines that maps into the same place. So that's why I need to first search through the tag and say that, oh, okay, this is the line that is stored, and then access the content, okay? Because content you cannot, it's a number, right? So you don't know whether this is the right content for you or not. You don't know the answer for that. Yeah. The address for now is going to be, yeah, the address that goes inside the memory will be 32-bit, yes. But the address is also some other complications that you're going to see later. So there is a difference between what we call a physical address and a virtual address. Your virtual address is always 32. Your physical address is the actual address that you need to, like, address the memory. That might be less or more. It depends on the design. So there will be a mapping there. For now, we just treat everything 32 bits. Yeah. One of the two. In this particular example, each row of the cache has one of the two. If you have 8 memory rows and 4 rows for the cache. Okay? So this is kind of like what we are trying to answer, right? So what is the right mapping that we should use? And how do we know what we have stored? For now, I just assume that one possible of mapping, which is I'm just using the lower bits to assign things to each of the lines. Later, we're going to see that this actually can be optimized, not necessarily needs to be this way. It could be other ways of the mapping. But at least we have one way of making this work. So we know that this is the mapping, this is how we store the tag, and this is how we find the data. Josh, you had a question? Yes. You can also have a valid bit that's saying that, okay, not only I stored this tag, but this is the data that I'm storing. Yes. But most of the time, when we're talking about cache, we're talking about cache when it's full. So you already have all the data inside. So you have something. But yeah, you do have a valid bit. Okay. All right, so let's actually talk a little bit more about the organization. What sort of mapping should we use, right? Uh, and see what is the best idea. What do you think should be the optimum mapping here? Like, do you have any suggestions of like what are some ideas that we can use the mapping? The one that I gave you already is like, look at the lower bits and then based on the lower bits, decide the mapping, right? So for example, if your lower bits is 101, 101, then you go to 101 in this case. If your lower bits is 001, you go to 001. So that's one way of mapping. What are the other ways of mapping? Anyone wants to suggest? Yeah, yeah. Okay, so you can play with where you do that 3 bits. So you can make any sort of different mappings of that 3 bits. So the upper 3 bits, like the most significant bits, maybe somewhere in the middle. That could be one way of doing it. Yeah. Any other suggestion? How do you guys decide where to sit in the class? What is your strategy? Yeah, yeah. You see the empty seat and you go and grab it, right? Yeah. Uh huh. You have somewhere there. Yeah. You what the view of your, yeah. So you decide like this some form of a distance maybe as well. So so one way could be this, right? You can just find that first available spot and just grab it, right? You don't necessarily need a mapping for the addresses. You can just find the first available spot and then and go for it. Any other suggestion? Yeah. You can like, yeah, I'm now mostly talking about like where do you decide even at the beginning, where how do you decide the mapping would work. So what you're saying is more on like what to keep and when to decide to when to like kick things out, which is we get to that point as well. But for now it's like what is the right mapping. Yeah. So yeah, so you find the best available spot. You do some form of a predetermined mapping. So these are the usually the 2 ways. The mapping itself could be different flavors. For example, you can do some form of a hash to find the mapping. So here I'm just doing it directly, right? I take the lower 3 bits and I find it. But I can also feed it to some hash function and then find that address, right? I can look at the higher bits, lower bits. I can do these tricks and each one will have some benefits in terms of locality, as we're going to see later. Or they can also find the first available. So what is the pros and cons of each one, do you think? You got a question? Memory would be, so you think that memory generally would be spread out? Yeah, so usually if you think about locality, it's probably what will happen is spatial locality tells you that if you access this, your next access is probably this. Okay. And also if you access this, this, and this, you most likely you're gonna repeat accessing them. So this is your temporal locality. So you want to do a mapping that accommodate this kind of sequential or spatial locality the most. They're not accessing the same cache. They're just mapped to the same one. I'm just showing you the mapping, saying that if I go with this algorithm that I'm looking at the lower 3 bits, this would be the map. I'm not saying this is the access pattern. Uh-huh. Why can't be what? Yeah, as I said, you can also grab, like, it can be no mapping at all, right? So empty cache, you start with just grab the first available place, right? So you have some mechanism keeping track of what is open and what is not, and go grab it. Actually, in fact, I'm asking you a question. What is the pros and cons of these structured versus unstructured way? What would be a good, why like unstructured would be a good idea? You want to answer? Yes. Mm-hmm. Yeah, 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 yeah. The bottom line is that you want to maximize the utilization of your cache, right? The bottom line is whatever algorithm that I'm using, I want to maximize the usage of all the rows. If I can maximize that, that's a good map. Okay. All right. But there is also one problem with like, this randomize that we're going to talk about. So first one, the one that you saw so far is called what we call a direct map cache, okay? As the name suggests, it's directly mapped. That is, you see the address, you use the index, and then you know exactly where you should go, okay? So I see the index, I see the lower 3 bits, I know this is where I'm going, okay? So everything is hard coded in some sense. It's directly mapped to that. Okay, and everything that has the same index goes to the same row. That's you actually hard coded into, you bake this into the hardware. Okay. Um, and as I said, there's the way that you would store the tag would be that you assign the index bit, whatever remains becomes your tag. Okay. Um, so this would be essentially how you would, for example, do it for an 8-bit address, okay? As I said, you have a tag store and you have a data store, okay? And as you mentioned, you usually have a valid bit in the tag store. So valid bit would be a 1-bit flag that is either 0 or 1. 1 means that I'm actually storing something useful here. 0 means that I'm not storing anything here, okay? So the way that we're going to access the cache, which we usually refer it as cache lookup, is the following. The address comes, and this address comes from the CPU side. In this case, let's say the address is 8-bit. What I do is that I divide the address into index and a tag. Since I have, for example, 8 rows in this case, I said log 2 of the number of rows gives you the index, okay? So in this case, I have 8 rows, so I have 3 bits of index. For example, let's say the address that is coming at the moment is 001001111, okay? Which means that the index bit in this case would be 7, which means that I'm going to pick the last row of this tag store, okay? So I pick this value, so I pick the valid bit and I pick the tag, and then I compare the tag of the address, with the tag that I'm reading, condition upon that valid bit is 1. If valid bit is 0, you don't check the tag. You just say that this is not a match. But if the valid bit is 1, you compare this tag with this tag. If this value are the same, you call it a cache hit. Okay, so this is a cache hit. If these two values are not the same, this is a cache miss. Okay, then additionally, if it's a cache hit, you also pick the same row in the data store and provide the actual data. So eventually, all you care is that data, right? You don't care about the hit and miss particularly. You want that data to come back to the CPU. That's what the CPU cares. But in order to know that this is actual data that I want, I need to make sure that this address is the address that I stored in this row. So that's why I need to first check the tag. If the tag matches, I bring the data. If the tag don't matches, then this data is not the data that I want. I need to go to the memory or to the lower level of the cache to get that data. Okay? To improve the latency, instead of serializing this process that I check the tag first and then I bring the data, I do this in parallel, which means that whenever I get the index, I read this value and I check the tag. If I know that the value is correct, I put some form of a mux here, okay? So the mux basically says that this is your data and this is maybe some garbage or some like 0, 0, or whatever we want to do it. And this would be 1 and this would be 0. So if it's a hit, then I basically pick the actual data. If it's a miss, then I need to handle the miss. We're later going to talk about how do you handle the miss. But essentially means that your data is not here. You have to go to a lower level of cache to find your data, which is a separate story. Okay? Any questions here? Yes. 2 bits from the index? No. So the valid bit is extra. So tag is, so this is 6-bit total. So this tag store in this case is 5 bits of a tag, because tag is 5-bit, and 1 bit of a valid bit. Okay? And what is the size of your data store? The size of the data store depends on what sort of memory is this. Usually this is 1 byte. Remember, it's like a byte, like we store 1 byte per row. It could be 32. It really depends on the design. Yeah. What determines the valid bits? So whenever I install a new line into my cache, I make the valid bit equal to 1. So it's initially, when the cache is empty, it's initially 0. You install new lines by bringing them from the memory. When you're bringing them from the main memory and put it in the cache, the valid bit becomes 1. Yeah. So question is, if I have multiple levels of cache, how do I search? We're gonna get to it. So depends. In some cases, you may need, you can actually technically look it in parallel if it's an inclusive cache, but usually it's sequential. All right, so as I said, this is one way of doing it. The other way, the like a completely opposite way of doing it, is completely free. So no mapping, no structure, just free for all. Find the first spot, search the cache there. Okay, so if I have something like this, imagine again the same example: 3 bits of data of address. This would be my main memory, and then this would be my cache. Okay. So now if I don't have any structure, what I can do is that essentially I can say that any of these lines can be stored in any of these cache. So here I can have A, B, C, D, all the way to H. I can have any of that. Okay? So in this case, what do you think we should store as a tag? Anyone? What should we store? How do we, so the tag is for you to distinguish between the addresses. What should be stored? Yeah. Say it again. Yes, you need to put the whole address, because as I said, each of these rows could be any of these guys, right? So I need to store the entire thing. So like if I store 110, it means that I stored this line. If I put 000, I store this line. So I need to put the entire thing here, because there is no notion of indexing. Anything could be stored anywhere. So I need to search the whole cache every time that there is a new access. Okay? So so essentially my data store, so this was the direct map in what we call, this is called fully associative cache. There is no notion of index anymore. There is nothing to be indexed to, right? It could be any of those lines. So you have to search them all one after another. So your entire address becomes the tag. So everything is tagged. Yes. How do you do the search for this one? I actually have slides. I'll get to it once I give you an example. I'll show you how do we do the search. Okay. So data store doesn't change though, okay? So the data store stays exactly the same. The size stays the same, because data store has nothing to do with how you store things. It just stores the content. But the tag store is different. And as you can see here, the tag store is 3 bits, versus in direct map, the tag store was 1 bit per row. So the tag store for a fully associative cache is much bigger than the tag store of a direct map cache. So it's one of the key trade-offs between a fully associative cache and a direct map cache. Direct map cache has a very small tag space, but a fully associative cache has a big tag store space. Okay. But let's see what is the difference between the two, like why one would be better than the other. Let's say I have a system like this, okay? I'm only showing you the tag and I'm showing you the tag and the data for this one, okay? So let's say I have a direct map cache and I have a fully associative cache. Let's say each one has 8 different rows, okay? And let's say your addresses are also 8-bit. As I said, each one has a valid bit. Both of them requires this valid bits because essentially you need to know whether the data that you're storing there is a valid data or not. The big difference between the direct map cache and the fully associative cache, though, is that direct map has index, but fully associative has only tags, okay? Since this is an 8-bit address and you have 8 rows, so the size of the index is log 2 of the address size, right? Which is equal to 3. So my indexes are 3 bits, okay? So if I have my address, the first 3 bits would be my index, which means the size of my tag would be 5 bits. So this will be 5 bits, okay? In the fully associative, though, this would be 8 bits because I don't have any index. So that's the difference between these two. The size of the data is the same. So, oops. The size of the data in both cases is the same. It doesn't matter which one you're using. Sorry about that. Okay. So now with this information, so now we have the tag size. Now with this information, let's see we have a pattern like this. 0, 1, 2, 8. I'm just showing you in decimal, but you can also translate this into binary, okay? So 0 means that it has 0, 0, 0, 0, 0, 0, 0, 0. So this is the address that we are adding. For direct map, the first thing that you need to do is figuring out what is the index for this data. In this case, it's 0, 0, 0, 0. So what you would store is this tag. So you would store 0, 0, 0, 0, 0. If I want to simplify this, I just store 0 here. I just show it as one number, okay? Excuse me. In a fully associative cache, I store the entire 8-bit here, right? Which is also equal to 0. So I put 8-bit there, 0-bit here, okay? So this is for this first address. For the second one, the index would look like this. The tag would look like this, okay? So what I would store in the direct map would be 0, 0, 0, 0, 0. Again, is equal to 0. But as you can see, the difference between this one and this one is that this is for address 0. This is for address 1. So their index is different. Their tag is exactly the same, okay? And by the way, the valid bits of these becomes 1. If I want to store this in fully associative, I also store the entire, like 1, 0, 0, 0, 0, 0, 0, 0, which is equal to 1. And I put 1 here as well, okay? Same story for 2. 2 becomes, again, 0, 0, 0, 0, 0. Valid bit here. This one be like this, which is equal to 2, and value here, right? Now comes 8, okay? So if I write down 8, looks something like this, right? So 8 is like this, which means that the index is 0, 0, 0, okay? Which means that in the direct map cache, I should go here. So already I have the valid bit equal to 1 here, which means that I have already stored something here. So I check the tag and I see the tag is 0. I check the tag, I see the tag is 1. This is called a cache miss, okay? So I need to, for direct map, I will kick this out and I put 1, 0, 0, 0, 0 here, okay? So I replace the 1 with, I replace 0 with 8. In the fully associative, though, since I have still open spaces, I do 0, 0, 0, sorry, 1, 0, 0, 0, 0, and I put valid bit here. I do not need to kick this out, right? Because I have still empty spaces. For direct map, even though I have empty spaces here, since this is mapped to the first row, I have to kick that out, okay? So here's where the benefit is coming from. If I have a pattern like this, 080808, what you will see happens in the direct map is that you first put 0 here for the first one, then 8 comes, you have to kick this out and then put 1 here, right? Because the tag is equal to 1. 0 comes, so this is, the first one is a miss, obviously, the second one is a miss. Then 0 comes, and again, it says that, oh, tag should have been 0, but it's 1, so this one is a miss, and so on and so forth. It's going to continuously, the same rows, they're going to, these addresses going to kick each other out. This is usually called conflicting addresses. They conflict in the same row in the cache, and they kick each other out. But if you actually look into the fully associative, you will see that the first 0 comes and you put it here. The second one comes and you put a 1 here and a valid bit here. Now this 0 comes and now you see that, oh, okay, I have it. So this would be a hit. This will be a hit, and so on and so forth. So actually after the first 2 accesses, the rest of the accesses will be all hits, okay? So if I compare the two, the direct map and the fully associative, you will see that direct map is very, very sensitive to conflicting addresses, the addresses that maps into the same row, versus fully associative very nicely can, as long as you have more rows, you can accommodate more of these together, okay? But the problem with the fully associative is that it needs more tag store, and there are actually other problems in the fully associative that I'm going to talk about. Any questions here? Yeah. Yeah, you go to the, in all cases, you go to a lower level of the memory or the cache and get the data. So always, we don't show that part, but yeah, if it's a miss, you have to go to a lower level. Okay. So let's actually, remember I told you that what we do care about is average access time, and average access time was hit time plus miss rate times miss penalty. So let's actually compare direct map with fully associative in these 3 categories. So let's start with hit time. Which one do you think has faster hit time? Fully associative or a direct map? Direct map, because direct map, you essentially, all you need to do is go into the one row, whatever that row is, and just search for one thing. It's either there or it's not there. For fully associative, you have to check all the rows. So it takes more time. Later, we're going to see that you can actually do it in parallel, so it's a little bit better, but still takes more time, okay? So hit time, direct map is better than fully associative. So the hit time of direct map is lower than the hit time of a fully associative, right? What about miss rate? Which one do you think has a lower miss rate? Fully associative has a lower miss rate because we just literally gave you an example, because fully associative can utilize this entire row very well, versus direct map depends on the address patterns. If your address are very conflicting, then you're not going to get a very nice utilization from your cache. Lastly, what about miss penalty? Which one has higher miss penalty, do you think? They are the same. So miss penalty has nothing to do with the current structure. Miss penalty means how much time does it take to bring the data from the lower level of the memory or cache. In both cases, they are bringing it from the same lower level, so the miss penalty is exactly the same, okay? So this is how it looks like. So usually the hit time of a direct map cache is much, much lower than a fully associative cache. but the miss rate of a fully associative cache is much, much lower than a direct map cache, but their miss penalty is almost the same. Sorry, exactly the same. You got a question? Yes. So the question is, can we somehow change the access pattern so that we reduce the conflict? Yes. At the software level, you know this column major, row major when you're writing. So that's exactly where you can actually reduce or increase the locality. So you have to know how you store things and try to maximize your locality with the way that you write your code. So if you're, for example, indexing addresses one after another, you can change the stride, for example, to make sure that there's like the conflict is less. Compiler can also do that, but many of these things are really hard to know during the programming, uh, uh, during the software stage before the compilation. So that's why the hardware usually takes care of these things. Yes, the compiler can also organize this. There's this thing called tiling, which you actually kind of make sure that you access things and you repeat accessing things more, and that way you can actually increase the locality and increase your hit rate. I never said that you don't prefer direct map, so it's actually direct map in many cases preferred to the fully associative. Uh-huh. You got a question? Very good. Any other questions? All right. So when you see something like this, the natural question is, can we somehow combine these two things, right? Because obviously direct map has a nice hit time, but it's a terrible utilization. Fully associative has great utilization, but terrible miss hit time, right? So is there a way to combine these two things so that we have the best of both worlds? And the answer is yes. This is called said associative cache. So you kind of like have a direct map, but you add what we call associativity to the direct map, such that you have semi fully associative cache, which we call a said associative cache. So how does it work? Remember, the direct map would look like this, right? So you pick the index, let's say the lower bits, you store the tag, and boom. And then fully associative was that, oh, let's get rid of the index altogether. Everything is a tag, right? So said associative will look like this, that let's have index, but let's have partial index. Within each index, have fully associativity, okay? So instead of having 4 rows, let's have 2 rows, but instead of having 1 column, let's have 2 columns, okay? So here's the idea that I'm gonna, since I have only 2 rows in this particular example, I only need 1 index bit, okay? So the lower bits decide whether I'm picking this row or this row. But within that row, I have 2 spaces, and I can store any of the 2. So it doesn't matter. So within each row, it acts like a fully associative cache. It can be the left one or the right one. There is no difference. But between the rows, there is a difference. So index decide the row, but within the row, you can choose whatever you want. As a result, the tag bits that you need to store is going to be the upper 2 bits, because the lower bits decide the index. You no longer need to store that. Remaining part would be your tag. So here you have 2 bits. And again, your data stores stays the same. So your data store doesn't change. The only thing that change is your tag store, okay? These 2 columns are called ways, okay? So this is called, each row is called a set. Each column, column within that row is called a way, okay? So for example, since this has 2 columns, we call this a 2-way said associative cache, okay? If I had 4 columns, then I call that a 4-way said associative cache, and so on and so forth, okay? So ways are the columns. If I have more ways, then I have more associativity within each row. And you can think about a fully associative as an n-way direct set associative cache. If I only have one row and all the columns are basically the entire cache, then that's a fully associative cache, right? If I have multiple rows, then I have a set associative cache. If I don't have any column and I have only rows, that's a direct map cache, right? So these are the three options that you have. So you either have one row and everything is a column, and that is your fully associative cache. If you have some rows and some columns, then you have a set associative cache. If you only thing that you have is just rows, then you have a direct map cache. Does that make sense? Questions? Great. So how do we do the lookup in a set associative cache? Remember I told you that in a direct map, I have a tag store and a data store, and I pick the 3 bits to pick it. For something like a two-way set associative, I'm going to have 2 tag stores and 2 data stores, right? So I'm going to have 1 tag store, 1 tag store, 1 data store, 1 data store, okay? So what I would do is that I take the index, which let's say that example is similar to the example that we had for the direct map. So I have 8 different rows. So I take 3 bits. Let's say the index is 111. I go to the last row, but since now I have 2 possible columns, I pick both of the tags. And in order to make things fast, I check them in parallel, okay? So I check them in parallel and OR the results. So if either of them is a hit, then it's a cache hit. If neither of them is a hit, then that's a cache miss, okay? And the same thing for data. I read this, and I use some form of a multiplexer to choose which one to send out, okay? And as I said, if it's a miss, then you need to actually go to a lower level and bring the data. Yes? So the question is, how do we pick between the left one and right one when we want to put something? It's the same story for the fully associative as well. Like, how do we pick which one? For now, consider it as a round robin. So you put left and then right and left and right. Later on, we're going to see a better approach for it. Other questions? Okay. So let's actually compare the same sequence of 0, 8, 0, 8, 0, 8 with a direct map and a set associative cache, okay? Again, assume that you have 8-bit address. First question, how many bits of the tag do we need? For the direct map, how many do we need? Anyone? 5 bits, right? It's the same story before. 3 bits for the index, remaining would be for, but what about set associative? 6, because this is 2 bits, right? Because I have 4 of these. So this is 2 bit, this is 2 bits, so this would be 8 minus 2, which is 6, right? And this is for the same size of the cache. If you compare the size of the data, you still have 8 rows of data on the set associative. You still have 8 rows of data for the direct map. So in terms of how much data I can store in these 2 cache, they're exactly the same, okay? But now let's actually look at the pattern. For the pattern for this one, we already talked about it. Oh, sorry. We already talked about it. Here I stored 0 for the first one. Then I need to kick this out and I store 1 for this one. Then I need to kick it out and store 0 for this one, and so on and so forth. So it will be a miss a miss, a miss, a miss, and a miss, and a miss. So all of them will be misses, okay? We already talked about fully associative as well. If you remember, said that the first time will be a miss. This one will be also a miss, but afterwards it will be hits, right? So it will be 4 consecutive hits because 0 and 8 both can exist in a fully associative cache without any problem. But then let's look at the set associative. For set associative, 0 comes. The first 2 bits will be the index. The remaining bits would be the tag. So in this case, it would be 0, 0, 0, 0, 0, 0. I store this into index 0. Okay, so I stored this here. Then 8 comes. 8 looks like this, right? And then this means that this is 2. So I store 2 here, right? Sorry. I store 2 here. And then 0 comes. And I see that, oh, I have 0. So first 2 will be missed. This 0 will be hit. This 8 will be a hit, and so on and so forth. So since I have 2 slots for the same index, now I can actually accommodate 2 conflicting addresses. If I had 3 conflicting addresses, there will be a miss, some misses, but at least I can accommodate in this particular case 2 conflicting addresses without any problem. So as you can see, the miss rate pattern of a set associative in this particular example is exactly the same as a fully associative, but the search is significantly more simple than a fully associative. Here you only need to search 2 things versus 8 different things. Yeah. The first 2 misses, yes, it's because you don't have the data. It's called what we call compulsory misses. That regardless of what sort of structure you're using, since you haven't seen this before, it's going to be a miss. All right. Yeah, so this will be the pattern. So let's compare this average access time between them. So remember that the direct map has the worst. Set associative is next, and then fully associative. Oh, sorry. It would be this way. Fully associative is the worst. Set associative is slightly higher than the direct map, but not that bad. It's kind of fairly equivalent. For miss rate, fully associative has the lowest. Set associative have slightly bigger, but close. But direct map is significantly larger. And miss penalty, same story as before. All of them would be the same. Okay? So this would be how things will look like. So set associative is a nice trade-off. It gets closer in terms of hit time to the direct map, but in terms of miss rate, it gets closer to the fully associative cache. Okay? Any question here? All right, let's have a quick break, and then we're going to talk about the next thing in caches. Okay. So far we talked about mapping. We understood the difference between direct map, fully associative, set associative, the difference between hit time, miss rate, and miss penalty. Let's talk about another very important thing, and that is what should we do when the cache is full or when there is a conflict and then we need to decide to kick something out. So yeah, let's say we have a scenario like this that we have 0, 1, 2, 3, 4, 5, 6, 7, and then 8 comes. For a direct map cache, if you compute the indices, you will see that the tags basically would be 0, 0, 0, 0, 0, 0, 0, 0, and everything would be 1 here all the way down to here. This would be for this first 8 addresses, okay? 8 comes, and you see that the index is equal to 0. You have one and only one option in direct map, and that is kicking out whatever is stored in the first row here, and you put tag equal to 1 and call it a day, right? So for direct map, there's not much of a decision. So if it's conflicting, you kick out the old one and replace it with the new one. And there's only one option. However, for the fully associative, things are different. So for fully associative, you store things like this, right? And all of the valid bits would be 1, right? But then 8 comes, and since 8 can be stored anywhere, now you have a choice, right? So you can kick this one out, you can kick this one out, you can kick this one out, right? Or you can pick any out, so you can pick this one out. So now the question is, which one should be kicked out? And fully associative and set associative is kind of the mixture of the two. So for set associative, if let's say you have a 4-way set associative, then you need to pick one out of these 4, right? So you have still a little bit of direct map, so you know which index. You cannot choose any random index, but within that index, you need to decide which one, okay? So now the question is that if I have option, like 8 option here or 4 option here, which one should I kick out? Any suggestions? Yeah. What's that? The top, the least recent. Why do you want to kick the least recent? So yeah, so if you want to maximize your temporal locality, you kick out the oldest one, because the idea is that you want to keep things that are like, you want to keep things as fresh as possible, right? So you assume that things have been used for quite some time. So between the newer ones and the older ones are the ones that it's less likely to be used in future. So you want them to kick those out, okay? So this is what we call a least recently used, or LRU, okay? So that is one option, that I do LRU. And by the way, this is called replacement policy, because we want to replace things with something else. The policy that I'm using is the least recently used, or least recently updated, and then kick that out. Are there other options? What are the other options? Yeah, just any option. Bad options. Most recently used. Okay. So what do you think would be scenarios that most recently used would be actually a good option? Because in fact, it's actually being used. It's not like, where do you think is the most recently used is a good option? If you loop back to the beginning, okay. Any other suggestions? Think about, yeah. Say it again. The tag has biggest gap, you said? So yeah, you want to you want to jump further away from the memory. Okay. So are you trying to answer like why you want to kick the most recent used one? Oh, okay. Uh-huh. Yes, you can also like look at the tags and then decide based on that. Uh, but going back to why you want to kick the most recent one, think about something like video streaming. In video streaming, do you rewatch the frames that you load? No. So your temporal locality terrible. Your spatial locality great, temporal locality terrible. So you actually don't want to keep things in the cache that much. Okay? You want to kick them out as soon as possible, because if I keep kicking this out, this provides opportunity for these guys to live longer, and then that might be useful, especially later when we are talking about multi-core. You will see that the cache is shared between different cores, okay? So there will be some cores that have lots of locality and some other cores that don't have that much locality. So techniques like this would be useful, okay? So in fact, actually, most recently used is not that bad of an idea in some cases. Any other suggestion? Yeah. Least frequently used is also good. So if I have some form of a counter that I can count and say that, oh, okay, this has been used many times, maybe I should keep that, even if it's old, right? So yeah. Least frequently used would be a complex things because now you need to have a counter and keep track of what has been used. That's true. Any other suggestion? Yeah. You can pick randomly, right? So you can pick randomly. The nice thing about random is like very simple. And you never know, actually, sometimes random works very well. If your patterns are random, picking random is also not a bad idea, right? So you do something that is not have very structured data. There is no structure to extract to begin with, so you may as well just do the random. Yeah. How do you pick randomly in hardware? I mean, so it depends on whether you're doing true randomness or pseudo randomness. In pseudo randomness, there are ways you can just shift registers and all. True randomness, you usually extract it from some physical behavior. For example, you extract it from temperature variance. There are actually hardware units that create randomness because randomness is very important for generating keys, like cryptography keys. So there's already there. Quantum sensors, for example, these days is very nice for creating true random number generators. But the separate story. All right. So deciding what to evict matters a lot, okay? Because, for example, imagine a scenario like this, that I have this patterns of 0 to 8, and I need to, for 8, I need to kick something out. And what I kick out is important because, for example, let's say soon after that, after maybe a few other addresses, I'll have 7, okay? So if my replacement policy had kicked out 7, this would be a miss, right? Versus if I do random or do other stuff and not kick out 7 and maybe like kick out 4, then I will have a hit, okay? So there is a direct relationship between what you kick out and your miss rate. So you want to intelligently pick things to kick out to reduce your miss rate. So a good replacement policy will minimize your miss rate. You cannot obviously make the miss rate perfect because you don't have knowledge of the future, but you will try to make your miss rate as low as possible. This is very similar to the prediction in some sense. So you're kind of predicting the future, right? So you're looking at these addresses, and between them you say that for some reason I believe that 4 is the one that leads into the lowest miss rate. It's very similar to the misprediction. In fact, we actually had, so there's actually a lot of work on picking the best replacement policy. There are lots of different research papers. We're going to talk about 2 of them here, but there's actually a whole bunch of other ones that if you're interested, you can take a look. And sometimes you also have a competition on replacement policy as well, similar to the branch prediction policy competition that is going on right now. All right. So now the question is, okay, what to evict and how to evict. The first option would be picking at random. The nice thing about random is very, very easy to implement. But if, of course, it's not utilizing the temporal or spatial locality as the way it should, right? So you can pick at random, great for design. And as I said, if your workload is also random, then it's not going to be that bad. But typically what's been used as kind of like the gold standard in the cache design is what we call LRU, or least recently used. In order to do the least recently used, you need to keep track of the age of each of the lines. So you need to know which one out of, let's say, these 8 is the oldest, okay? So for that, you need some form of a storage for that. The downside of this is that this comes as an overhead because you need to also now store that metadata, that kind of position within the cache as well. So it kind of eats up the useful storage that you have in your cache. But if it leads to better miss rate, then it's worth it. Okay. So usually in order to kind of implement LRU replacement policy, we introduce this additional column that different people call it differently. We call it position. Okay. So how does it work? Let's say I have a fully associative cache, and let's say I have a pattern like this. Okay. So let's say initially this is all of these bits are valid. So let's say initially I had a pattern like this, and now I'm doing this after that. Okay. So let's say originally the position looks something like this, that this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7, which 7 means that this is the newest. So higher means that it's highest. Okay. So now what's based on that, let's say this is the sequence that I'm seeing right now. So the first address that comes is 1. Okay. So 1, I have to check, is it in the cache or not? I go to, I need to search in the entire cache. I see that, oh, okay, the second one is 1. So this will be a hit, and I can move forward. The important thing about LRU replacement policy is that even if it's a hit, you have to update the positions because now 1 is the most recently used. Okay. So what I do need to do is that I need to change these positions into a new position. The way it would work is that now 1 has to become 7, right? So now 1 needs to be promoted to the most recently used. So the position for this guy needs to be 7. So now that since this is 7, everything has to be adjusted accordingly, right? So this used to be 7, now this has to be 6. This used to be 6, this now is 5, 4, 3, 2, 1, and this one was 0 and it stays 0, right? So think about it as a queue, right? So you pick 1 out of the queue and put it in the front of the queue. Everything else kind of shift upwards, right? So this will be the new position for this. Then 2 comes, right? And again, you will see that the 2 is actually in the cache. So this will be also a hit. But then you also need to, again, update the positions. Now 2 needs to become 7, and everything else will be adjusted, right? So this would be 1, and then 2, and then 3, and then 4, and then 5. Any questions so far? Okay. So now 8 comes, and I look into the cache, and obviously there is no line that is equal to 8, right? Which means that now I need to kick something out because there is no space. What I do kick out, what I'm kicking out, I'll look into these positions and I find the oldest, the one that has 0. So in this case, it's this guy. So I need to kick this out. So I change the tag and I put tag equal to 8 here. And I'll also update the positions again. So this becomes 7. This becomes 5, 6, 0, 1, 2, 3, and 4. Okay? So this would be a miss, but then I'll update and put 8 here. Okay? Okay, so this is also gone. Now 9 comes, and again, 9 is not here. It is a miss. Which one should I kick out? The one with 0, right? So in this case, it's this line I need to kick out. So I put this as 7, put this as 5, and 4, and 6, and 0, and 1, and 2, and 3. And I need to update this tag now, right? So this 3 becomes 9. Okay? Then 4 comes. 4 is a hit. This becomes 7, and everything else will be updated. 3 comes and 3 is not there anymore, right? So 3 comes and 3 is not there anymore. So this would be a miss. And I need to find whoever is 0 and replace that and so on and so forth. So the story kind of continues, right? So you any new access that comes is either in the cache. If it's in the cache, you update and promote it to the most recent one, and then you adjust the rest. If it's not in the cache, you find that it's 0, you kick that out, you put that instead of like you update the tag, you promote it to the most recent, you again adjust everything else. Okay? Any questions? Yeah. You don't need to, you can switch. The switching usually is very expensive. So you can actually have some form of a bit. So like a 3, so for example, in this case, I need 3-bit data, right? The problem though is that if this is large, then the number of bits is pretty large. So you need to actually store so many bits to maintain the position. You're also searching for the ones that you need to kick out is very time consuming as well, because now you need to search through the entire rows one by one to find the one that is 0. So LRU is great in practice. Sorry, it's great in paper, but not the best design in practice, because has lots of overhead in terms of storage and in terms of searching and in terms of power. Okay? So what do we do instead? We do what we call PLRU or pseudo LRU. Okay? So pseudo LRU basically says that instead of having positions, let's have just 1-bit flag. And this 1-bit flag is mainly just saying that whether I used this before or not. Okay? So the way it works is that initially everything starts from 0. Okay? It means that I haven't used this before. Okay? Then if I access any of these lines, I make that flag equal to 1. It means that I use this. Okay? Then whenever I want to kick something out, I start from the top, or I can start randomly, but usually I start from the top and find the first one that is 0, and I kick that out. Okay? If all of them are 1, okay, if there is a scenario that all of them has been used, then I will pick one at random, or I start from the top and kick it out. So either one. And then I reset everything back to 0. So it's kind of like one round, everybody has been used. So I reset everything again and I start from there. Okay? So essentially you start from 0. On a hit, you set the bit to 1. On a miss, you find the first row from the top with flag is equal to 0. If all bits are 1, so you cannot find the 0 bit, you reset everything and pick the first row, or you can also pick at random, doesn't matter. Okay? So that would be the algorithm that you choose for pseudo LRUs. This is one way of pseudo LRU. There is another one that has a tree LRU, which we haven't talked about, but this is called an MRU, or not used bits, basically replacement policy. So when I say PLRU, this is what we mean. So essentially, we just have 1 bit to keep track of this. Is this as good as LRU? Obviously not, because there is some approximation, but it's very close. So in fact, actually, people have shown that like up to 90% accuracy when you compare an actual LRU with a pseudo LRU. But the nice thing about this is that the overhead is very, very low. Just 1 bit, very quick to search, and very easy to handle. Yeah. So the question is that how does this why is it very close to LRU? Because essentially what you are doing here is you want to keep track of what is being used, okay? And there are many lines that are they call dead on arrival, which means that they are just one-time use. Okay, there are many lines that are dead on arrival, which means that their bits is not going to be ever set to 1, and this is very good at finding those guys. So there will be lots of memory addresses that are being used and they quickly become 1, but there are many lines that are not being used at all, and this is great at capturing that. And as a result, majority of situation, lines that are not being reused, they will be kind of bubbling up and then being kicked out. Yeah, it's 0. Yes, it's flags in when it's used. Yeah. You can also actually, I'm gonna like in the next slide, I'm gonna talk about. You can also, so these are all different policies. You can also try to bring it and put it as a 1. That's also possible. That actually goes back to the overall algorithm for any replacement policy. So I gave you 2 examples, actually 3 examples: random, LRU, and pseudo LRU. Any replacement policy can be defined by these 3 things. The first one is install. What should we do, or where should we put this replacement policy? And should we put it as MRU or LRU or somewhere in between, right? Update means that what should we do for on a hit? Should we promote this to MRU or should we not promote this? And when it's full, what should we do? Who should we pick and replace? Answer to these 3 questions will give you any replacement policy. And as I said, there is like 6 or 7 different replacement policies that being actively used in modern processors. The difference between them is like a tiny bit of difference between each of them. You can like change how you update, and that would be a new replacement policy. Okay? So you can actually like think about these 3 questions for LRU, random, and PLRU. And as I said, there's a whole bunch of others that are kind of similar in a sense with this. Questions? Okay. So from the rest of the lecture, I want to talk about optimizations in the cache, okay? So you kind of understood the basics. You understood the mapping, the storage, the replacement policy. So you kind of the basics and fundamentals of the cache, you know everything about it. From now on, I want to talk about how do we further optimize the cache, okay? So first of all, for replacement policy, there are a whole bunch of different things that you can do. So you can, approximate, you can make it adaptive, you can make it hybrid, and also keep in mind that whether or not your replacement policy is a good replacement policy also depends on the active or access patterns. For example, if this is only this computer is or this memory system is only used for streaming data, then you want to pick a replacement policy that doesn't really care about temporal locality. But if it's just a general purpose computer, you probably want to have temporal locality or spatial locality. But there's a whole bunch of, as I said, this is also very active space for different types of replacement policy. The impact of replacement policy on average access time is that replacement policy helps you with reducing the miss rate in most cases. If the update scenario is also pretty complex, your miss penalty might also increase. Replacement policy usually do not change the hit time because hit time is just searching through the cache. It's just nothing to do with what you do with the replacement policy. Replacement policy happens in the background. But the most important things about the replacement policy is reducing the miss rate if you have a good replacement policy, okay? The last thing about replacement policy is the type of misses that we have in a cache, okay? There are actually 3 types of misses that you have in a cache. In fact, there's actually 2 more that later on we're gonna see it. But for now, think about any miss in the cache is one of the 3 things. The first group is what we call a compulsory miss that I described earlier. The compulsory miss means that the first time I see a particular address, it has to be a miss because cache starts empty. You don't like pre-initialize the cache. So the first time that I'm accessing a particular address is going to be a miss. Doesn't matter which replacement policy you use. Doesn't matter whether you're using direct map or fully associative or set associative. Doesn't matter how big your cache is. In all cases, your compulsory misses stays the same. Okay? Then you have what we call a capacity miss. Capacity miss means that if you had a fully associative cache, and if you still get a miss in that fully associative cache, that is called a capacity miss. Okay? It means that just generally your cache is small. So for example, if I have an array that requires 10 kilobytes of data, it has 10,000 different rows, and my cache is only can store 1,000 row, regardless of what you do, you're always going to have capacity issues. You're not going to be able to store all the 10,000 at the same time. So whatever you do, you're always going to have some misses. And lastly, you're going to have what we call a conflict miss. Conflict miss is just because of direct map or set associative. It's when you're actually, your index are overlapping to each other. For fully associative, we don't have this problem, but for set associative and conflict miss, you have that problem, okay? So one issue with direct map and set associative is having the conflict misses. Capacity miss, you will have it in all the caches, okay? Any questions here? Perfect. All right, so the last thing that we're gonna talk about for the rest of this lecture and probably a little bit of the next lecture is optimizing the cache. Look at this formula one more time. Hit time, miss rate, and miss penalty. If I want to optimize my cache, what I can do is that either improve the hit rate, improve the miss rate, or improve the miss penalty. Any of them I improved the overall design of my cache. So let's actually talk about each one by one. So let's talk about miss rate. How can we reduce our miss rate? Any suggestions? Some of it we already talked about, so you can actually say it again. Yeah. If you increase the size of the cache, you will reduce the miss rate. That's one way of doing it. Yes. Anything else? Yeah. Better replacement policy, reduce your miss rate. Yes. Have a set associative or even better fully associative cache, reduce your miss rate. That is also true. Anything else? Well, I mean, the ultimate version would be fully associative that doesn't have any indexing, right? So, but yeah, better indexing also helps. Okay. The first thing, so all of those things that you said is correct, and we're actually going to get to it. There's actually like few 6 or 7 different ways that you can increase, so you can decrease your miss rate. The first one is what we call a block size, increasing the block size. What does it mean? It means that in order to reduce the miss rate, if you have lots of spatial locality, it's a good idea that you bring more data to your cache from the cache to the CPU, because that will reduce the future accesses to the cache. So think about it as the library example. When you're bringing one book, maybe you bring other relevant books with you. That will reduce the times that you need to go back to the library, right? So increasing this the block size is helping with reducing the miss rate. What is a block size? Essentially, so far I told you that each row, think about it as 1 byte, okay? But you can store more bytes per row, okay? So if I have more bytes per row, I call this row a block, which could be 4 bytes, 8 bytes, 32 bytes, 64 bytes. It could be big block sizes, okay? Uh, the nice thing about this is that when I'm reading 1 byte, I bring all the other bytes with it as well. So now, for example, think about this as an array. Not only I'm reading the first index, I'm also reading the entire next 63 indices as well, okay? Uh, but keep in mind that you still want your CPU to be byte level. So you want your memory to be byte level. So usually we introduce this thing called block offset, which is still, if for example you have 4 bytes within your block, you need to be able to distinguish between the individual bytes in your design. So that's why you need a block offset. Okay. So your design, so your cache address in that case would look like something like this. That, remember I told you that your cache has an index and a tag. Now it also needs to have this thing called block offset. Okay. So this would be how your cache, for example, would look like, okay? So let's say, for example, your addresses are 32 bits. This is the address that is coming from the memory. Let's say you have a direct map cache. Your direct map cache has 8 different rows, okay? If it has 8 different rows, then you need 3 bits of index, okay? And now let's say that your block size is 8 bytes, okay? So it's not 1 byte anymore, is 8 bytes, okay? What does that mean is that if I still want to have a byte level granularity, I need to be able to select which of these columns I need to pick, okay? So since I have 8, log 2 of that, I need 3 bits of a block size as well, okay? So this would be a structure of my cache. Each row now is not just 1 byte, is 8 bytes, okay? And I have 8 of these rows. That means that the total size of my cache is 64 bytes, okay? And then the way it works is that I need 3 bits to pick the block, and this is called block offset. So essentially you're offsetting from this block. I use the index to pick which of these rows I want to pick, and the remaining bits would be the tag. So since I have 32, 3 bits for the block offset, 3 bits for the index, that means that I have 26 bits of the tag, okay? So this is the tag store, 26-bit. I choose the tags, I pick the block offset, I pick the final byte out of this. So every address is still 1 byte, but I can now read the whole thing into 1 row at the same time, okay? Similarly, for a fully associative cache, I no longer have index, so I only have tag, and I have block offset. Still the same thing. If my blocks are 8 bytes, then I need 3 bits of the block offset. The remaining 29 bits would be my tag. And then one thing that we usually do to optimize this is that we do this in parallel. So we do all the 8 checks in parallel, okay? And lastly, if I have, let's say, a 2-way set associative cache, I have 4 different rows. So as a result, I need 2 bits of index. I still need 3 bits of block offset. The remaining bits, which in this case would be 27, would be the tag size of my design. So the tag size would be 27. And this would be way 0, way 1. As I said, this whole thing is called a set. And yeah, that would be basically the design of this. In all of these cases, the storage size is 64 bytes. So my data store in all cases is 64 bytes. But as you can see, the tag sizes and the structures are slightly different. Okay? Another way of showing this is this thing called CBS. So CBS is essentially showing you, these are 3 numbers, okay? So for example, you say, someone says that, oh, this is like 28, like 8, and like 4 or whatever. This means that essentially each of these tells you what is the size of each of this. So for example, instead of showing you this picture, I can give you the number for C, B, and S, and you will be able to basically redraw this picture, because essentially B says how many blocks, how many bytes you have per, how many bytes you have, how many blocks you have per set. B tells you how many bytes you have per block, and C tells you how many bytes you have in general in cache. Okay, so this is kind of like the way that you can show this different design. This is just an auxiliary thing, so it's just one way of showing a design of the cache. Just FYI. Okay, so now going back to reducing the miss rate, I told you that one way of reducing the miss rate is increasing the block size. Okay, if I increase the block size, instead of only bringing 1 byte, I can bring 8 bytes together or 16 bytes together. And the nice thing is that if I have nice spatial locality, this will increase my hit rate, basically. Okay, so now the question is, how big should be the block size? Should I bring large block size? Should I bring tiny block size? Should I bring medium-sized block size? How do we know what's the right size, and what's the pros and cons? Anyone wants to say? Yeah. Yeah, exactly. So block size is good, but you don't also want to bring a lot of blocks. So essentially what will happen is that if I plot the miss rate over the block size, you will see a pattern like this, that your miss rate initially decreases as you increase your block size, but there will be a minimum. At that point onward, you're going to essentially pollute your cache, because you're going to bring a lot of things. Let's say, for example, you're bringing 64 bytes, but your spatial locality is, let's say, is only 8 bytes. That you're only reading the first byte, second byte, all the way to 8 bytes. You're not going to read anything beyond that point, but you're bringing a lot of things. And remember, when you're bringing things, means that you're kicking something out. So you are potentially kicking things out that could have been useful. That's why your miss rate is actually increasing, because you are occupying space of some other potentially useful data in the cache. So block size, increasing it is good, but you have to increase it such that it doesn't pollute your cache. Okay. The second thing that you can do to, and by the way, one thing before going into the second item is the difference between bandwidth and latency. Okay. In cache design, in memory design, when I say latency, it means that how long does it take for me to bring one block of data. This could be from L1 to L2, from L2 to L3, and so on and so forth. The time it takes to bring that one block. Bandwidth means how many blocks can I bring at the same time. So if I have a memory design that has large bandwidth, you probably want to bring lots of blocks, okay? If your memory design is low bandwidth, then you don't want to bring lots of blocks, okay? So it's important. And how do you decide this? This is purely technology. So newer technology like DDR4 versus DDR5 versus DDR5E, I don't know, enhanced and whatever, or DDR6. The difference between them is this, that they have higher bandwidth, they have lower latency. You probably also heard about high bandwidth memory, or HBM memories. So those are type of technology that can bring a lot of data at the same time. So it's like a lots of pins that you can bring lots of data at the same time. Just keep that in mind. Okay, going back to reducing miss rate. So first thing we learn is increasing the block size helps you to some degree. Second thing that we already discussed is associativity. Fully associative is better than set associative, is better than direct map, okay? So, but you also want to wonder that how much associativity is good. Like, if I want to pick a set associative cache, how many ways should I choose? Should I choose 4-way, 8-way, 16-way, 128-way? What is the right number? And actually, again, if I if I plot the cache size with the miss rate with different number of ways, I'll see that if I increase the number of ways, the miss rate will reduces, but at some point it's going to be flat. That is 16 and 32, it's not going to be any different. And more ways means higher hit time. So your hit time actually increases. So you want to find the minimum number of ways that gives you the maximum decrease in the miss rate. Okay? So that's why if you look into modern processors, you will see that usually you see either an 8-way set associative or a 16-way set associative. You would rarely see anything beyond that number or anything below that number, because that's usually a good trade-off between the two. Just keep that in mind. The third thing that can help you, or the fourth thing, or I think it's third thing, that can help you with miss rate is obviously the size. Lower the cache, higher the cache size, more data obviously you can store, lower the miss rate. Now the question is, how big should be your cache? Does it mean that anytime that I increase my cache, I'm going to get better miss rates? Is there any points that this is not true anymore? You think it's not, right? Well, in fact, it is. There are two reasons that you don't want very, very large caches. Number one is large cache means higher hit time, because essentially the way these things are designed is larger cache has higher capacitance for reading, so your hit time unfortunately increases. So you only want to increase your cache size if you're truly getting benefit in terms of miss rate. And what you will see is that at some point you're going to get diminishing returns as a result. The other things that you will see is you will be limited by compulsory misses. Compulsory misses, it's not going to help to have larger cache if you have lots of compulsory misses, okay? So you cannot get benefit by just making your cache bigger and bigger. Most of the time it helps, but not all the time, okay? How do we fix the compulsory misses? This is the last thing we're going to talk about. So actually, there is one way to reduce the compulsory misses, and that's the idea of what we call prefetching. So the idea of prefetching is guessing the future patterns. Very simple one is something like this. If I show you this pattern, what do you think is the next address? I plus 4, right? So it's very easy to predict. So instead of saying that, oh, okay, I don't have this, I don't have this, I don't have this, I don't have this, and let's wait for I plus 4 to come and say that, oh, sorry, compulsory miss, I haven't seen it. You can prefetch the data. So your cache, your higher level cache can ask memory proactively before that access to happen and ask for that data. This is called prefetching, okay? So basically for prefetching, you need to first predict the pattern, and pattern like this is actually quite common. And once you do that, you need to actually request that data. So usually there is a hardware unit called a prefetcher that exists in the higher level of the cache that issue a new request to a lower level. So from the lower level, it thinks that this is a legitimate request. It provides the data, but in fact, it's actually initiated by the memory. It's not initiated by the CPU. Yes? Yeah, you can bring, so for example, for blocking, if I bring I and my block size, let's say is 4, I can bring I plus 1 and I plus 2 and I plus 3 as well. And this is actually reduce the miss rate for these guys. But what I can do on top of that is I can maybe also prefetch I plus 4 and the block with it. So plus 4, 5, 6, and 7. I can be also very aggressive and also bring 8, 9, 10, and 11, right? So I can mix and match all of these together. So I can bring blocks, and I can also prefetch these blocks. Yeah. So blocking is static. That is like I never bring just one byte. I always bring the block, whatever that block is defined in my design. But prefetching is dynamic. Yes, prefetching is dynamic. So prefetching, good thing about it is it reduces the compulsory misses. The bad thing about it is that if you are not great at predicting prefetching, you also cause cache pollution, similar to the block, right? So if you think that, oh, this is the one that I need, and in fact you messed it up, you're going to bring things into the cache that you're not going to use. So you need to kind of decide on how much aggressive you want to be with your prefetcher. There are some designs that are very aggressive and bring things a lot of time. There are some other designs that only make sure that I really need this and I can bring it. And there are these dynamic approaches that you can, for example, get some feedback about like how useful these lines are, and then you can adjust the aggressiveness of your prefetchers based on that. Essentially, for prefetchers, you need to answer 4 questions. What addresses to prefetch? When should we initiate the prefetching? You don't want the prefetchers to be too soon. You don't want your prefetcher to be too late, right? You want the data to be right at the same time that you're accessing it. You need to also decide where you want to put your prefetcher data. Do you want to put it at L1? Do you want to put it at LRU? Do you want to put it at MRU? You want to put it somewhere in between? And then how does your prefetcher operates is also important. We have software prefetchers. We also have hardware prefetchers. We have hybrid prefetchers as well. Okay. This is where I'm going to pause. I think Tuesday next week is a holiday. So we're going to continue this on Thursday next week. Okay.